So I'm going to work back to Hess's law. So what we're doing today is we're working towards, it's going to take all week, we're working towards what is the yield of a reaction. And I kind of messed up having you do a question on the problem set before I got to today's lecture. Again, a bit of a screw up on my part, so you know I make mistakes, so I do feel bad about that, but I can't really fix it. Okay, let's go back to Hess's law. Okay, where we're trying to calculate delta G of a reaction. Delta G, because at constant pressure and temperature, negative delta G is positive delta S total. One of the questions a lot of you missed, right? That's why we told you in high school that delta G needs to be negative, because generally constant temperature and pressure conditions are common, and when temperature and pressure are constant, then minus delta G is positive delta S. That was the answer to that question. Anyway, okay, so we're talking about delta G of a reaction, and I wanted to point out, I do this in the book, that this is basically integrated. So, okay, this is kind of wrong. I hinted to you that, really? Okay, so I hinted to you that the way we did Hess's law, it's fine, but it's actually not really true. Now, and let's take a more advanced look at what you're actually doing. All right, what are you doing? You're always solving for, we have a big delta, then we're integrating a little delta. Fine. What are the limits? The limits are, of course, in the initial state, we have reactants, and of course, in the final state, we have products. Okay, and then the result is products minus reactants, just like you've known since high school. But as we have gone over and over and over again, there must be something quite wrong with this, or not the full picture. I'm using some shorthand. Okay, there we go. Now remember why we use delta G of formation. It's because we don't know what the true intrinsic G's are. We do not know the real absolute Gibbs energy of a molecule because it's too hard to know. So we use a relative delta G of formation. That was the answer to another question. Unfortunately, a lot of folks missed that one. Okay, so again, this is how we're analyzing the delta G of a reaction. We're at constant temperature and pressure. For this, from now on, we're at constant temperature and pressure. And negative delta G is good. That means total entropy increases. Total entropy increasing is what's really in charge. That's what really makes something spontaneous. And this is how we told you to do it. Okay, still, hopefully nothing has gone too wrong in your minds. Let's look at G. And let me bring up a new representation of a reaction where we have all reactants. I'm just going to say react for reactants and prod for products. Okay, so we have this parameter that goes from 0, the reaction hasn't started, to 1, the reaction is finished. And if I do this calculation, you can imagine I might have this situation, or I might have this situation. So delta G is positive or negative. Okay, now if we have, let's do this bottom case. Okay, so delta G is negative. That means that if instead of reactants I have products, there is more total entropy. Okay, now my question to you is, what's the reaction yield? 100%?
It's all products.
Now if I have all products, according to this, if I have all products, the universe has more entropy than if I have all reactants. So now tell me, what do I have? All products or all reactants? Which is it? What do you think? Now the question is, if we just look at this very, reactants minus products, if this is all there is, and we get a negative, we do a Hess's law, high school Hess's law, and we get a negative delta G, this is what I've drawn. Again, this is like just a diagrammic way to express energy as a reaction goes forward. Do I have all products or all reactants?
You would end up with all products.
All products, because that makes more total entropy, right? Now, if delta G is positive, then I have all reactants, right? Okay, and that's correct based on what we've taught you. Okay, now remember I told you think of the streams. What if the delta G is minus .0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000oo .000000000000000000001. What do you think? All products are all reactants. Minus .00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000I said minus .00000000000. I sound like a dog, don't I? All products are all reactants. Well, all products in the negative case and all reactants in the positive case. Does that not bother you? What if delta G is minus 400 million billion trillion mega monkey joules? It's the same as minus .00001. That doesn't make sense, does it? Right, so this Hess's law picture of what delta G is wrong. This is actually wrong. It's not wrong quite so much, just to put it this way, it's just not the whole picture. Now, here's what we're going to find, by the way. Okay, let's do a negative delta G, because that's obviously a bit more interesting. Here's what you failed to consider. That there could be something in between. That's what you didn't consider. Okay. When you did Hess's law in high school, you just drew a line between the two, but that's not how it actually works. All right, now the way to analyze what the real delta G is, what we're going to do is not integrate dg. What you're going to do is integrate something like this. It's kind of clever, right? You're going to integrate the slope of this line. Now, the way that looks graphically for you graphical people, which is not many of you, I'm always surprised. This is not a very graphical class. It's fine, and I adjust. You notice I only have one graph question. Okay, so let's think about what that looks like. The way I've drawn it here, so you can see what happens is that, for one, reactions have finite yields. You know that. That's the problem. You know that if the reaction is minus 400 million billion trillion monkey joules, that you want to have more products than if it's minus .0001 joules, right? It makes sense. And here's why. The things bow downward, and your most negative delta G might be somewhere in between, giving you not a perfect reaction yield, just like basically almost no reactions except like burning gas and stuff. Some things have full reaction yields, but not many. Okay, now if you analyze it this way, what you do is you look at the slope, and it's really fun. I love doing things this way because it's simple, right? Because you see how I'm still measuring delta G. You see how I'm integrating delta G. But now look at how it ends up working. Okay, so I've got a negative turning to a positive slope, and so that kind of looks like this. Based on what I've drawn here, so negative, then it becomes 0, and then it turns positive. So you notice how I did that, and I had it crossing 0 at about the same point. You notice that? Here, I need to put a little epsilon there. Okay, so again, I've just drawn the slope, and then the delta G is the area. Right. Now, notice what happens is you get the most negative delta G if you integrate to this point. You do not integrate the reaction yield to 100% because you gain this area, which is positive. All right, you see how I did this? How if I'm integrating this thing, this is dg. This is dg. I've just re-expressed it. You can see now that dg gets more negative as long as I integrate up to this point. But if I go further, which is to say that the reaction yield keeps going to completion, I actually start to go backward. I start adding to g. Remember, that's bad. We want negative g, not positive g. We let the integral run to here, and then we stop it. That's the most negative g, delta g. That is the most entropy. If we allow the reaction to keep going, we start losing entropy. We're gaining entropy, then we start losing it. So the reaction won't do that. The reaction stops here because it knows that delta G starts raising, meaning delta S starts dropping. Total S starts dropping. Total S dropping never happens. Right, so anyway, so this is just kind of a graphical way to see big picture what we're doing. All right, so anyway, big picture, Hess's law doesn't work because, as you knew it in high school, because it draws products to reactants like this, Reality is the thing can bow downward, and you can see hopefully when we re-express it this way, again more of a mathematical via graph, why going to this point actually gives you the biggest negative delta G. Okay, now what we want to do is, and I'm still reminding you, but I'm throwing in some more details about why this didn't work the way you thought it did. Okay, the next thing. We then introduced, as I mentioned that we were moving away from this, I introduced the idea of chemical potentials. So we had kind of this weird stop. Minus SVT plus VDP. Okay, so we had this weird stopping point, and I started talking about right before the exam, chemical potential, which is when, not that I have a hole in the magic cylinder, it's when reactants start reacting. So I start losing moles. Oh, but of course they form products, so I gain moles. Okay, if I'm going to start changing mass, it is the same thing as there being a hole in the magic cylinder, but that's kind of a stupid problem. Why would I care about that? When I let moles change, it's because I'm doing a chemical reaction, because now I can study chemical reactions. Okay, now there are some nuances to this. Okay, in a constant P and T world, these are gone, and we gave the DG, DN a symbol for chemical potential. That's the chemical potential symbol. So we introduced chemical potential. Again, we're always working with delta G. We're always at constant T and P, and you see why? You see why? It simplifies things. It simplifies things. So let's work with this. It's already complicated enough. Let's make it easy. Okay, then we did ice melting. Ice melting, and what we found was that DG, which had to be negative, is composed of ice, and the number of moles, I'm using different symbology because I want to make this easy, but this isn't proper. So we have chemical potential of ice, we have a certain number of moles of ice, we have a chemical potential of liquid, we have certain moles of the liquid, and this has got to drop, and that's because the number of moles of ice it's melting. So remember, again, I know it's been a while, it's been a week. Ice in a bucket, it was at equilibrium, but then I turned up the temperature, so the ice is going to melt, and of course, for every drop in ice, you gain the same amount of liquid. You have to have that for obvious reasons. Okay, then what we found was that the chemical potential of ice minus that of the liquid, remember it's all H2O obviously, we have to have this relationship, and we know that the ice is dropping. That's negative, this is negative, and that means that this is net positive. And therefore the chemical potential of ice is greater than that of the liquid. Okay, now again, this was actually kind of trivial to solve, however incredibly powerful. This is one of the most powerful things I can show you. It says that when the proper terminology, I don't like this description, it's too highfalutin for me. Mass flows from high chemical potential to low chemical potential. That's the highfalutin way of describing this. It just says that, your reactants have high chemical potential, your products don't, right? So the chemical potential of the products is lower than that of reactants. Reactants have high chemical potential. They then turn into products which have lower chemical potential. So anyway, that's how I like to put it. And this is proof of that. Now remember also that as much as ice melting is rather boring, it is a chemical reaction. No different than we'll start with A goes to B, and then we'll move on to O2 plus H2 combusting. We'll move on to octane combusting with oxygen. We'll move on to real chemical reactions, but this is technically a chemical reaction. So if H2 and O2 form water in a big boom, it's because H2 and O2 had high chemical potential and the product water had less chemical potential. I also explained this in terms of phase diagrams, and I'm kind of just being overly repetitive, so let me just move on from here. Okay, now the reaction stops. This is where ice melting is not a great analogy for what we're about to. I think it's a great intro, but it doesn't really follow through too well. Why does the reaction stop? Because the chemical potentials are equal. Okay, so now big picture, what we're trying to do, we're going to work on this till Friday. What we have to do is connect what you learned in high school for Hess's law which hopefully I've now shown you, what's wrong with that? I can't talk to you. I've shown you is not, there's something not quite right with this. There is more to this than meets the eye, for the reasons I talked about before about how you get all products or all reactants with any value of negative delta G. That can't be right. There's more to this. Okay, now I've also just showed you, really this is at the other end. So this is the beginning and this is kind of the end. And what we want to do is connect the two. This clearly had more to it. Figuring out how the chemical potentials of products and reactants are equal is the end. It's the end of the reaction. When I know how to do that, the reaction is over, and then I can calculate the reaction yield. That would be the point of this course. What else could I show you how to do except calculate the yield of a chemical reaction? There really would be nothing else of value I could ever cover. You come up with something else. Well, what's something about the cats? I don't know. But this is the most valuable thing it can teach you. So how do I go from here to here? Right now, remember, there's something in between, right? And that's what we're going to cover because this is truly our endpoint. All right, now, before I do that, before I start adjusting this for chemical reactions, only to figure out how we make those two equal because that's our stopping point, I have to find where I put this. Okay, before I even get into chemical reactions, we even have to stop there. We have to stop there and take a breather. Not go out and vape. What I actually mean is, okay, this is kind of interesting. This is one of the more interesting things about this stuff, just to show you why this Hess's Law stuff is not quite right. Okay, so now we are going to do all gas phase reactions just because it is easier. Actually, I think I alluded to this a little bit on, Monday? Yeah, on Monday. And I asked some of you some questions. You actually gave me exactly the answer I'd hoped for, although it wasn't quite right for various reasons that I'm going to go over now. Okay, now, A and B. Now we're going to do chemical reactions in the gas phase. And I'll show you a little bit in about a month about how you figure out chemical reactions in the liquid phase, but we're going to do gas phase. Okay, now I've got thermochemical data for A and B, and they'll react to form C. And I've got all the delta G's. I've got all those numbers in the table in the back of the book. You know what I'm talking about. CP, delta H, delta G formations. S, not delta S, S. You know what I mean? You had them in high school. They're in the one little table in the book I wrote. It's a little janky, but can't help it. It was free. Okay. Now, if I'm going to get them to react, the first thing I have to do is I have to mix them together. Oddly enough, now you know that. Now, here's my question to you. Now, so I'll have a little partition. And I'll just open it up. So that they have to mix. And now we won't let them react. We won't let them react. They just have to mix first. How can they react if they don't mix together? And this is the part where this goes completely off the rails. As much as this is childishly simple, thermochemically, we've gone completely off the rails. Okay, initial state. Now, we know that we're going to use what? What do we use? What's the thermochemical data we have for A? What is it? Knowing that we don't know the true intrinsic G, we use the formation G. We'll assume that we have 1 mole of it, so we'll use the per molar value. Okay, and this is of A. And then this is the thermochemical data we have from the table in the back of the book is for B. Assuming that we have 1 mole of it, so we look at the per molar value, so those are the same number. Okay, is that correct? And we're at SDP, we're at P naught, 298. Remember that those little knots, those now mean something different. Those mean standard temperature and pressure, 1 bar, 298. Okay, now, is this the right number? Are these the right numbers? Okay, now I have pure A, pure B. I have 1 mole of them, and they're at SDP. What is the thermochemical data I have? Is it this? Now, I have all that. I have all on the table. I'm just asking, is this the right number? Am I working with good numbers? Yes. Everything's fine. What about here? No. No, no. These do not apply here. No. The delta G's have changed. Nothing happened. I didn't let them react yet because I have powers. Nothing has reacted yet, but as soon as you remove that partition, the thermochemical data has changed. Now, one of you said correctly, and I meant you, it was you, right? Yeah, I think it was you. I said, how do these change when you go here? And, and I said, if it's a perfect gas. And we'll make them a perfect gas. They haven't even reacted. So they haven't changed, right? And I think you said yes. Right, perfect gas, so they don't interact.
Yeah,
Right?
So they're still like the A and B, and they're just kind of floating around.
Yeah, they don't interact with each other. Well, again, that's because they're not reacting. I haven't turned on their ability to react. And I wanted you to say, and you did say based on what you knew, that these data actually should translate. They should be, the energy constant, the G should all be the same. And that was actually what I wanted you to say, but it's actually not true. So again, the point of this is that those numbers in the table in the back of the book apply to pure chemicals, but you can't react to pure chemical, because what the hell? All right, if you're going to react something, you're going to add something else. And as soon as you add something else, those numbers in the table in the back of the book are now wrong. I haven't even gotten to the reaction yet. Okay, fortunately, we're going to deal with this. And then we're going to let them react, and then we're going to figure out how these are equal. So again, step by step. Now, how do I adjust the values just for the simple act of mixing? That's mostly what we're going to get to today. We won't get much further than that. Maybe a little bit. And so to do so, because they are perfect gases, they're perfect gases now. We'll turn on their ability, so they can't react if they're perfect gases. We'll just like turn it on by magical means, the force or whatever. Let's see, what do I want to say? Okay, let's figure out what it means to mix. Now there has to be a change in Gibbs energy for mixing. Mixing is like a chemical reaction. So what I can do is say that the process of mixing, and it will be at STP, this would not be, as soon as you have multiple things, that per molar goes away. Anyway, okay, so what is this? Okay, so this is, and I'm not going to use really proper terminology. This is the Gibbs energy, will always be at STP, so I'm always going to have that little circle. Maybe I'll forget it sometimes if I screw up. So we have them in the mixed state minus the pure state. Okay, so there we go. Now, it has to be true that what happens is negative. The reason is, see, this is why things have to be different. A and B mix. Now, do you think they unmix? They'll never unmix. Once you mix A and B, you're pretty much screwed. It would be very difficult to ever, it is possible, of course, to remove gases. It takes tremendous effort. When you mix A and B, let's make it hydrogen and oxygen. I'll put some flesh on the bones. They're mixed, and for all intents and purposes, they're mixed forever. That means that this has to be negative quantity. You know things mix. Gases definitely mix. So we have to have a negative delta G. Now here's another way of putting it. The chemical potentials of A and B have to drop. By the way, those are the same things. That this is negative, or that the chemical potentials of A and B in the mix of the hydrogen and oxygen, when they mix, their individual chemical potentials drop. Those are the same thing. All right, so again, I'm trying to connect to this whole idea of chemical potential. Okay, so anyway, so this is what we're trying to do. Let me re-express it this way. So kind of forget this. Because I'm gonna just, I wanted to just kind of put this in a product, like product minus reactant type of way. I wanted you to kind of look at it that way. But let me calculate it a different way. Let's see what, let me do for A, which will be like hydrogen or whatever. Okay, so A in the mixed state is going to be A in the pure state, I called it like that, minus the integral of its change of G. Okay, now delta mix for species A, this is the total. For A, I'm just going to bring that over here. Delta mix A minus the number in the table in the back of the book will just be the integral, plus, right? Plus the change. The change can be negative. It will be negative, in fact. Sorry, never assume that. You always add energies. If they happen to be negative, that's their own business. Okay, so let me bring this over. Okay, in the mixed state minus A in the pure state, I know I'm kind of creating some symbology, is the integral of dg. And dg will be minus the entropy of A times the change in temperature, but we're not going to let the temperature change. The volume of the box times the change in pressure, but the pressure doesn't change. Plus, oh, wait, sorry. Mistake. I get ahead of myself, I get excitable, sorry. Okay, this is kind of neat. Okay, temperature won't change. Number of moles won't change, because I haven't let it react yet. Okay. Did the pressure change? Yes. Did the pressure change? Who said that? Yeah. What? Okay, hold on. One bar. The whole thing is what? 1 bar. What do you mean the pressure changed?
The partial pressure.
The partial pressure, right? Because I have a little symbol here, right? You have to keep it down to species A. The partial pressure changed. Okay, how does the partial pressure change? Okay, so now what we have now is that the notice now that I'm calculating how for A. I'm just doing A. I'm going to do A and I'll add B on later. So this is, again, it's like hydrogen and oxygen. We haven't let them react yet. You know it takes a spark to do that anyway. So A's chemical potential, or its G, which are the same thing, are going to drop. All right, how so? It is going to be the integral of it's a partial pressure. And I'll put a label on that. Okay, now, here's the thing. Initially, it was at 1 bar. And then later, it'll be at some reduced partial pressure. Because you know that when you're dealing with a perfect gas, and let's put it in a liter, and it doesn't interact with B, and all of a sudden, see, from A's perspective, when this partition is lifted up, because it doesn't see B, it rushes into the right-hand container. Right? You see, it's basically doing work. It moved into this new container. It doubled its volume. And so there's some work energy. And energy is energy. So, VDP. And let's see here. Now, I'm going to have to remember that the volume is going to track pressure as NAR, and again, T is constant over the pressure of A, dPA. And this ends up being NART ln. Partial pressure in the mixed state and the initial pressure. In the initial pressure, we have to make it 1 bar. So again, we're going to be reacting things. We'll always be at 298 and 1 bar. We'll worry about changing that later, like a month from now. But there you go. Okay, now again, big picture. In the beginning, A and B are going to react to make C. I need thermochemical data. I have that in the table in the back of the book. I have the delta G's of formation of A, and I have the delta G's of formation of B. They're at 298 and 1 bar. That's fine. We're gonna put a clamp on that, and so we won't have to worry about 298 and 1 bar. Except when we first allow them to mix, for all intents and purposes, this partition opens up, allows A to wander into B space and B to wander into A. So that means that A's partial pressure will basically half. It'll be half what it used to be. And so I can see that NART ln, is this ratio here, is that greater or less than 1?
Less than 1.
Yeah, it'd be about half, right? Now, maybe it's not a perfect gas, but let's say it is. Let's say that this is a liter, that's a liter. So this is about half. What's natural log of a half?
It's a negative number.
It's a negative number. So delta G, so this number in the table of the back of the book, when it mixes, drops. Delta G became negative. That's why it mixed. It wouldn't mix otherwise. Okay, so now, Now, let me simplify this further, but now I need to, again, this is where the weirdness of this room and this weird board work against me. Normally, I would just like move the board up and keep working down, but I can't. Let's use Dalton's law. Dalton's law. I think I talked about this on day 2 of this class. I don't quite remember, but hopefully you remember the way this works for partial pressures of gas. You should have had this in freshman or in high school. What you do is you look at the mole fraction of a species times the total pressure. Now remember that I had 2 partitions. One was at 1 bar, the left was at 1 bar that had A, the right was at 1 bar that had B. So again, let's say that their behavior is relatively okay. So I opened up the partition, it's still 1 bar. And that means that the new partial pressure would be the mole fraction times the total. Again, hopefully you saw this as a high school thing. Okay, so then what? That means that in the mixed state, the process of A mixing, again, we're at the standard state, is NaRT ln mole fraction of A. And we're going to do 1 mole of A, 1 mole B, reacting to make 1 mole C, just to make things easy. And so this would be half, and so it's negative. So the delta G of A has dropped. It wants to mix, but you know it mixes. This all makes sense. Okay, now what we have to do is that then I have to do a big therefore. Now just listen to me because I'm not going to write this down. Now I want to do this reaction, this mixing reaction. Again, we're still working with stupid reactions. Melting is a reaction, kind of, yeah. Is mixing a reaction? Actually, yeah, it can be. So the total mix, here, let me total. So I don't want you getting lost in your notes, like where the heck did this come from? What I'm doing is I am going to add in the results of A and the results of B. And of course, if they're negative, that's their own business. We always just add energies. And that's part of the first law. Okay, so we got Na, RT, ln chi A. And again, you know, I'm not going to write all this out because it's stupid. Everything for B has just got a B on it. It's NB, RT, ln chi B. There you go. Now remember the natural log is technically, this is like a work term. When these things expanded, when A expanded into B space, it was technically like doing work, and of course B expanded into A space. And you know that brings up a natural log, and that's an energy term. So there you go. Okay, so this is the thing. Now both of these are negative, so the net, so it's net negative. Okay, now what I want to do is I'm going to do some factoring. I'm going to point out that the number of moles of A is its mole fraction times the total. And the same for B. Okay, too many, I'm not doing brackets too well. So there you go. Okay, I just factored out the total number of, really? I actually know who most of you are now, by the way. Okay. All right, now I am almost halfway to being able to determine how far a reaction yield occurs, meaning I'm almost ready to actually turn on the reaction. What I'm going to do is then divide both by n. And then what I've got is the change in G per mole. What's the word for that? What's the end goal? To connect this Hess's law to the change in chemical potential. What's the chemical potential? Yep, hold on. Let me remind you. I'm going to re-emphasize this again, but you kind of a little bit slipped off here. Chemical potential is the change in G for the change in number of moles. But these being extensive, they can be integrated. So this is the G over N, which is the G per mole, which is chemical potential. So the change in chemical potential for mixing, I need to put in this little mix. Sorry, if you're having trouble seeing this, I'll rewrite this. Is RT chi A ln chi A plus chi B ln chi B. Okay, there you go. Yeah, question.
Is that the total change of?
This is the total. Now, so remember, this is why I don't want you getting confused about. I think you can follow me now, but if you read your notes, you're going to get confused. So try to make that clear, or watch the videos while I have these freaking things. I tried to focus on A up until this point, just because I don't want to, let's just do one thing at a time. And then the total is add in A and B, and then that's everything. And then I'm down to here. So this is the total. If mixing is a reaction, this is the delta G. Question.
Is that supposed to be mu integral dg at the end of that, or?
Now remember that chemical potential
I'm talking on the other side.
is mu.
Oh, so that was supposed to be erased. The rest
Mu,
of it?
mu. Right, and I just want to point out that when you have partials of things that are extensive, they can be integrated. So it's this kind of neat trick. I know maybe you haven't seen that before. I don't think I saw that until I took this class. Okay, now here's the thing. Now let me graph this, and now let me point out what is actually really in the driver's seat. This would be the kind of explain words question. Okay, let's look at, okay, so I'll do delta mix G, always at the standard state. I may forget that little circle there. Okay, let's graph this thing, and let's plot that as a function of chi A. And so this is, ooh, no, this is kind of messed up. What am I doing? Okay, so how do I describe this? I probably shouldn't be talking about this yet. What am I doing here? Well, I have to admit, I'm a little phenomenologically messed up about what am I trying to describe. Okay, here's what I want. Here's what this is. Regardless of what, now remember that what we're going to note these chi A's and chi B's are, they are going to be a function of the setup. Did I have a mole of A, a mole of B? Well, then these are a half. Did I have 90% A, 10% B, and then they mixed? Well, there's your chi A's. And then chi B is 1 minus that. Did I have 90% A, 10% B, 90% B, 10% A? Anyway, what happens is, depending on how you set the thing up, what you find is that you get a curve like this. You get a curve like this. So, and the lowest you can get per mole, so change in chemical potential is 1.7, and that's a kilojoule per mole. Okay, so if you want to have the maximal oomph for mixing, what this graph shows is that you want chi A to be half, right? So the most mixing punch you can deliver is to mix equal parts, and that kind of makes sense. The way to have nothing happen is to either have nothing to mix with, either have no A or have all A, but then you have no B. All right, so it took me a while to kind of, you see how I just said that? It actually took me a while to figure it out, to say that, because I figured out all the time. Anyway, okay, again, if you want this mixing to occur, the most oomph is generated when you have equal parts A and B, and that will give you a minus 1.7 kilojoule downhill to mix. But if you have no A to mix with, well then delta G is 0, but you have all B, so what the hell does that do? If you have all A, then correspondingly you have no B to mix with, and again there's nothing to do, but that's why the delta G is 0. So there you go. Okay, last bit. Now why, as much as I hope this is all straightforward. I've really not done any calculus, like barely any calculus. And what I've really done is, in the big picture, I took the number of the table in the back of the book and I added the work energy. That's basically what I did. And so and it's become a little bit more complicated. That's all that's happened. But now let's take another more interesting look at this so that it makes actually a bit more sense, because it's kind of gotten big at this point, and when things get big, they get a little bit more confusing. Okay, now let's think about mixing this way. And I will not do this per mole. And we'll worry about when we go off SDP some other time. Of course, we'll be at 298. Okay. Now, I haven't let things react yet. That'll be on Wednesday. Oh God, you people are gonna. Okay, I'm gonna give you your test back. I'm hoping. I told you there might be a little bit of a hiccup. I'm gonna try to give you your test backs Wednesday. Don't go crazy on them. All right. Anyway, I'll show you how to adjust this for reaction. We're really close to reacting. We just won't quite get there today. All right. So I've let A and B mix. I've let A and B mix, but not react. Who's doing that? Really driving me nuts. There's one of you up there. Anyway, so I will not let these react and I make them perfect gases. So what do you think? It's your turn to talk. So, what's the question? What do you think? What's driving this? What do you think? Zero.
Enthalpy zero.
Enthalpy zero. Okay, we're going to do perfect gases, and they're not allowed to react. Now, when that's it. I think it was, anyway. Now, remember, we haven't let it react, so we're going to say the gases are perfect. So, if they mix, why would any heat be given off or absorbed, right? Because they're not changing. A is not interacting with B. It's not even interacting with itself. So why would its energy change? Why would its internal energy change? Or at constant pressure, its enthalpy change? Why would it change?
Because it did work.
Well, no. The answer is no. No, it doesn't change. Yet there is a delta G. What am I putting on delta G?
The change in entropy.
Yes, this is entirely an entropically driven process. Now, hold on. Doesn't it make sense? Mixing is entirely an entropically driven process. Wouldn't you have guessed that? But now doesn't it make sense? Because these things don't interact. Questions?
Is it because we have more combinations of where the molecules can be, or
In terms of a K, B, L, N, W, yes. Yes, they have more microstates because they have greater volume. Now, that means that delta S mix, S, is minus NR. Notice that there's no T. I'll genericize this for more than two species. So this is more than two. I'm going to try to make this more and more generic. Eventually I'll go to a reaction like A plus B goes to C plus D, because it's nice to do A and B, but that's a little overly simple. Okay, and I had to put this per mole. 5.5 joules per K for mixing, and again I'll do this in terms of like an A and B. Okay, again, if there's nothing to mix with, there's no entropy of mixing. But again, the most entropy, now hopefully this makes more sense. The way to increase entropy is to have the most mixing. The way to mix things the most in an A plus B scenario would be to have equal parts, right? Because if you start to balance that more towards A or more towards B, it's intrinsically not as mixed. And hopefully that kind of intrinsically makes sense. So if you're at the halfway point, you get the greatest positive entropy of mixing, but of course if you have no B to mix, or no A to mix with, or no B to mix with, then nothing happens. So hopefully that makes sense. Well, here, we got to finish up. So anyway, all right, hopefully this makes sense. If not, I'll catch up on the videos. We'll try to do that today. Next time are actual chemical reactions, and then on Friday, we'll do chemical reaction yields.